Okay, so welcome to the third review session. This is actually a really important one, and not necessarily the easiest one either, so glad you guys came. Okay, so you guys know what the fundamental theorem of calculus is. It's this rule here. But a lot of people, after doing 1,000 problems or 50,000 problems, realize that it's probably wise to memorize it like this, actually. Okay? Even though it's exactly the same thing, what's happened is we've added this term over to the other side. This term here. So why would we do that? Well, I'm not saying you have to memorize it this way, but it's not a bad way. It's a good way, and here's the reason. We remember that the integral, the definite integral, always gives us a change in the antiderivative, right? So, for example, if this was a velocity function here, this would give you a change in position, right? If this was an acceleration function, it would give you the change in what? Velocity. Exactly. So, since you're not usually interested in changes, but rather final results, it makes more sense to isolate FB. So this would read more like this. Watch close. If we go with the red, it reads the final velocity equals initial velocity plus the integral of acceleration. Like this. dt. Okay? That's actually the green, yeah, sorry. So let's say you took the green on the left and you rewrote it there. The final velocity would be initial velocity plus the integral of acceleration. Of course, it's a definite integral between the two times t initial and t final. So this is just super handy. Like if somebody, let's say, says, oh, the acceleration is, 5t plus sine t or something, and you know that the initial velocity is, 3 meters per second or something, you can actually find the final velocity by doing this. You just go, oh, final velocity is just going to be 3 meters per second, because that was the initial velocity, plus the integral of 5t plus sine t dt. And let's say that this happened all between the first 10 seconds. See? So you just integrate from 0 to 10. This gives you the velocity at the 10th second. So it's just a little bit more practical. Instead of setting change in velocity, you get that final result. This would also work with position. So you could say like the final position is original position plus integral velocity. And being a physics major, I used this second version here way more than this one. Just because I was always interested in final results, Okay, you guys have any questions on that? Like what I mean by that? Okay, great. Michael, you're good? Okay. All right, let's go down now to this next part. It says the first fundamental theorem of calculus is sometimes also called the total change theorem. So there's more than one name for this thing. I've actually heard several names. The accumulation function. This thing is sometimes called the accumulation function. Total change theorem. Actually, the left side is called the accumulation function. Total change theorem. Whatever. Lots of names for it. But the reason is because it always gives you a change in the antiderivative. So it's got some different names. Okay, let's look at this first question. So the question is just asking you what this integral might mean. If w of t is the rate at which a baby gains weight after birth, and w is measured in pounds per month, and t is measured in months since the baby's born, how would you interpret this integral? Like, what would this integral even mean? That's the first question. Okay, so those really good answers. So we're going from, you have to understand what everything means. This means t equals 0 months to t equals 1 month. And this is measured in pounds per month times dt, which is d months. It's like an instantaneous change in months. So just from units alone, without any actual calculations, we can see exactly what this means. The months and the d months cancels out. You're left with an integral that's going to give us pounds. So evidently, the outcome units on this guy are pounds at the first month minus pounds at the 0th month. That's what it would mean. Okay, so now let's talk about a baby who is pounds at the end of the first month minus pounds at the end of at the 0th month is negative 0.127. What does that mean? So we want to actually construct a sentence here, not write more math, right? So this integral means what? Remember, this means pounds. We just figured that out. It's technically change in pounds. The baby changed his pounds in the first month. This baby lost weight. Yeah, this is very common. When you have your baby, you will find that it loses weight the first month. You don't want it to lose too much, but it'll gain weight again, right? You do keep an eye on that, though. You don't want to lose your little person, right? Okay, so this means the baby lost 0.127 pounds the first month. Okay, we have to be a little bit careful here. Like displacement, we can't take this too literally, okay? So, for example, this doesn't mean that the baby lost weight the whole time during that first month. Like every day lost a little bit of weight. You can't interpret it that way. In fact, the baby might have, this would be really weird, the baby might have been born, and then the first week gained like 10 pounds, became this big, ugly, like fat baby, and then lost 10.127 pounds over the next 3 weeks, and was down from his birth weight at negative 0.127. So we can't take it too literally. We just know that the change in weight was 0.127 pounds and lost. So actually our sentence, we should probably even tidy it up a little more. It means the baby lost a net weight of 0.127 pounds. That just means anything could have happened, but in the end it was a net loss. A net loss. So it's really important that you word it correctly. So let's squeeze in a couple more words. The baby lost, oops, just maybe the baby lost the baby's net change in weight was a decrease of 0.127 pounds. Okay, and then the next one, what does that one mean? What do you guys think the next one means? So, okay, so the baby's net change in weight, you guys know I'm not that eloquent, so net change in weight was a gain of 9.7 pounds, and you're really supposed to put the time in here, so see, I already forgot. I should have put the first month for the first one, and the first year for the second one. Okay, so they actually will ask you questions like this. The test has the verbal side. Like they'll ask you, what does this mean? You have to write it out. Okay, and then let's look at this next one. Let you read it. Okay. You got to really watch the units, right? So I like what Michael did. He was actually thinking about the units before he tried to answer the question. That was a good idea. Alrighty. So what are the units of F here? Dollars per year, it's given, right? And then T is measured in years. Always check that. So this would be dollars per year times years. This is a dollars integral, right? It's a money integral, obviously. So what kind of money? Change in money, right? It's change in money. Okay, so this is change in dollars. How many years have gone by? 13. Okay, 13 years since what? Since birth. You got to read it carefully, right? So the question is saying that the teacher was born in 1965. So time 0 represents 1965. Time 13 represents 1978. Right? Okay. So this represents 1965. This represents 1978. The teacher's 13 years old, and his salary is $0 more than it was when he was born. Is that reasonable? Does allowance count? Not if it's rate of earnings. Well, actually, I don't know. That's a good question. Technically, a child could earn a little money. Yeah, it's true. Hi. Hi. Here you go. No problem. We're just working through the first page. Okay. So let's discuss what it means first, and then we'll decide if it's reasonable or not. So this means the teacher's earnings, change in earnings, probably should use change in earnings, between ages 0 and 13 was 0. The change was 0. So I guess it doesn't necessarily mean they didn't get any allowance. It just means that maybe it never changed. Their change in earnings was 0. Right? So maybe they got $5 a day every day, or $5 a week just from their parents every single week until they were 13 years old. The change in earnings is 0, right? Integrals don't give us values. They give us a change in value, like a displacement. They don't give us a distance, right? Okay. Is it reasonable to say that the integral from 0 to 40 is 1,000,000? I think that first one's reasonable. I don't think a 13-year-old earns too much more than they did when they were 0. They probably don't earn anything, right? Is it reasonable to say that the integral from 0 to 40 is 1,000,000? This is $1,000,000. That's what it means. This is $1,000,000. We already figured out the units. I'm almost 40. I'm 39. Okay? Is it true that next year my increase in earnings, or my change in earnings from the time I was born might be $1,000,000? Teachers aren't the highest paid people in the world, right? But by the time they're 40, their change in earnings has been $1,000,000. We don't know where the money went. Right? It's not talking about expenditure, right? This is reasonable. I'm sure I've earned $1,000,000 at some point. Like, I don't know where that money is right now, but that's not what it's asking, is it? The total earnings, not the total salary. No teacher makes $1,000,000 a year. That's not what it's saying. So this is collecting or accumulating all my money throughout the years. I'm sure I've been paid a total of $1,000,000 by now. Okay? Okay, so the second one's reasonable too. Okay, the next one, be careful here. What do you think it means to have the 1 over 40 minus 0 out front? What does it mean to have the 1 over 0 minus 40? 40 minus 0. What does this extra part mean? What do we normally call the part down here and the part up here on an integral? limits of integration, or just a and b, right? Can you think back to any theorems where there was a b minus a down here? Where have we done an integral divided by the interval? Yes, mean value theorem. That's actually when you set this equal to f of c and you try to find c. Integral over interval is the average value of a function. Okay, so I'm glad you guys came to this, because that's really important on the AP test. Whenever you see 1 over b minus a, and then you've got the integral from a to b, this just basically gives you the average value of f. This is a very, very important theorem. Some people think it's the most important, one of the most important theorems in all of calculus. Okay? I don't know if you can say such things, but they're all important. All the theorems are important. But what about this particular case? The 40 and the 0 and the units and blah, blah, blah. What does it mean in this problem with the teacher? Okay, between 0 and 40, the average earnings. Earnings is measured in dollars. Are the units really dollars here? Let's check. Let's check, okay? So we kind of have to do this step by step. We've already decided that this integral spits out dollars, right? Okay, so that part is dollars. What are the units on this guy? Yeah, 1 over years, right? 1 over years. So this is years. So what are the net, or what are the units overall here, technically? Dollars per year. So we can't say it is average earnings, because that has the wrong units. Maybe do like an average, what? It is average. Average what? It's the average of f, right? Look back at the instructions. Average of f. What was f measured in? Dollars per year. Yeah, so it's the average change in dollars per year. It's my average change in salary. So I'm the teacher, right? It's my average change in dollars per year. Or average, it's the change in my average rate of earnings. Or average of f, which is average rate of earnings. Very important. If you don't have that rate, the word rate there, and you don't write the units in dollars per year, they will not give you full credit. And you still have to include in the first 40 years of life, or between years 0 and 40, or by the time they were 40. Say something about the time domain here. Okay, a honeybee population starts with 100 bees. It increases at a rate in prime. What does 100 plus 0 to 15, integral 0 to 15 in prime represent? Final what?
Population.
Final population of the bees. Yes. So this is an example of what we saw up above. This is initial population, and you're adding on the integral of bees per week d week. Right? So the week cancels out. You're adding on extra bees is what you're adding on. So this must represent final bees. Final population of bees. Obviously measured in bees. The units are bees. All right, a cup of coffee is put into a 20-degree room when T is 0. Coffee's temperature is changing at this rate. Find the coffee's temperature after 10 minutes. You can use the exact same thing that you just did. Initial temperature plus integral of R of t dt over the 10-minute period should give you the final temperature. Okay? So what was the initial temperature of the coffee? 90. Then you've got your 0, you've got your 10, you've got your -7, you've got your e to the minus 0.3t, you've got your dt, you've got your calculator. Where's the 20 degrees? It is not important to us. Listen, this is important for understanding the problem. Not every given is useful to you, okay? This little model right here, this little RFT right here, was designed with a room temperature 20 degrees in mind. So this equation wouldn't even be true if it weren't for 20, okay? So whoever created this little rate model for us was using the 20. But we don't need it for what we're doing. That's really important to understand that. Okay. So we're not using that 20 at all. The rate model includes that somehow. I'm sure it's buried in the 0.3 somehow. Give it a try. Type it in. Joseph, you typed it. What'd you get?
Oh, I don't know.
Okay. So the cool thing is your calculator can do all this, right? You can just basically do this right from the home screen. So you can just type 90, right, plus math 9. I get the old school notation. And then to type in your function, -7 e to the -0.3. You can even use t if you want, but I just usually use an x. And then you go comma, independent variable, x, comma, 0, comma, 10, and enter. And the answer is 67.828. 67.828. Hopefully you have the better software. Looks a little nicer. Was this one multiple choice? No? Okay, so just 67.828 on that one. Is that what I said? Degrees Celsius, right? They're very strict about that. You have to include the units on everything. And remember, if it's Kelvin, you don't write degrees. Although I've never seen Kelvin on the p-test. Just something to remember. Okay, let's go down here. This is kind of the same exact thing, really. These are multiple choice. Okay, this one says the rate at which water is being pumped into the tank is this function. T is in minutes, R of t is in gallons per minute. Okay, so T is in minutes, R of t is gallons per minute. We're being asked for the number of gallons. How many gallons? So probably should integrate, actually. That's how we're going to get gallons per minute and minutes to cancel. So integrating would give us, it says first 5 minutes. That just implies 0 and 5, doesn't it? That just screams 0 and 5. First 5 minutes. Stick in your function. This should do it. You might say, well, what about like gallons initial and gallons final? Not important. It's saying that we're just checking how many gallons were pumped in. So it's not like how many gallons are in the tank. It's how many gallons were pumped in. So we assume that at time 0, no gallons have been pumped in. So just go ahead and integrate that. You should get your answer. Which one's the best answer? D. Okay, thank you. All right, let's go to the next one. The rate at which ice is melting in a pond is given by this, where V is the volume in cubic feet, T is the time in minutes. What amount of ice has to melted in the first 3 minutes? So this is what we call a differential equation, right? This is a diff EQ. And we do different things with differential equations. But the easiest thing we do is just integrate both sides. And that's exactly what we'll be doing on this problem. Especially since they ask for an amount of ice, which is a volume. So integrating both sides like this with a dt will effectively give us integral dv and it's a definite integral from time 0 to 3. The left side just gives you volume. So I'm being a little informal here, but just type in the right side. Don't get too excited about doing it by hand, okay? Don't try to show off during the AP test. Nobody's grading your multiple choice work. Get the calculator out, punch it in. I don't think we really know how to grade this anyway. But definitely don't try to show off. There's no one to impress here. Just get the calculator out. All right, so what's our best answer on this one? E? Okay. I don't have my calculator handy for it, but I'll take your word for it. E it is. How come we're not like adding anything to this or whatever? It's because we're not really interested in like a final amount. We're actually asking a change in melted ice, and we're assuming that the initial amount of ice that has melted is 0, because they didn't tell us how much ice had melted at time 0. So if there's no other numbers, there's nothing else to do, right? So, let's go on. This one's the news broadcast. Probably the same thing, right? You just integrate. Let's set up the integral first, then we'll check to see if it makes sense. So probably in Mr. Lynch's class last year, if he ever gave you any word problems, you probably just took the derivative on everything. On the AP test, I found that if you integrate just about everything, that's probably the right thing to do. So my brother-in-law and I have a joke. If you're doing a new calculus problem and you have no idea what you're doing, just take the derivative and set it equal to 0. It's not really true, but on the AP test I found if you integrate most of these functions, it gives you something meaningful anyway. So let's set it up first, then we'll talk about what it means. Imagine integrating this. Right? And you would need time limits. But just units alone, what is it going to yield? R is measured in dollars per month. T is in months. So this is going to give you what? Dollars. Are we asked for dollars? Change in income. Sounds like an integral. Okay, perfect. I think we're doing the right thing. Like I said, setting up the integral is just the right thing to do. Now it says during 2007, and T is measured from January 1st, 2007, measured in months. So how many months are there in 2007? 12. So you would actually need to integrate all 12 months to get the full year effect here. So you're going to put a 0 and a 12 here. Here the limits are sort of implied but not stated, so you have to really think about it. During 2007 is a full 12 months. Time 0 is January 1st. So you're good. Type it in. What do we got? I thought it was 400 and something. Can't remember now. Can you give me some pennies on that? 80 pennies? Okay. See, in 2007, I don't remember earning that much extra money. According to this news broadcast in 2007, my income is increasing this much each year. I haven't seen it. I don't know where it is. That never happened to me. I guess I'm not the average American. Okay, let's go to this next one. This is a tougher one. Quite a bit tougher. So which expresses the change in altitude of the balloon during the time the altitude is decreasing. Oh man, you gotta watch your units. Why don't we set up the integral and we'll see if the integral is giving us the units we're looking for. This is kind of what we did last time too. Let's just write this down. It's probably the right thing to do, right? 0.8 maybe? Is it that simple? Is the answer just D? Okay, be careful, okay? First let's check our units. Make sure we're even doing the right thing, right? How is the rate function measured? What are my units? Yeah, it doesn't actually say. We assume that if it's a motion problem, then any derivatives or any rates are measured in something per time, right? Okay, so why don't we just make up a distance unit? Let's just say that this is measured in meters per second. That would be a great rate, right? Okay, so we're going to assume that this is meters per second and that this time is seconds. This is going to give us a change in meters. Is that what we want? What is this question asking for? We want it to give the change in altitude. That's the change in meters? Okay, we're doing a great job here. The only thing is, the balloon has been traveling over the time interval 0 to 8. That doesn't mean it's been decreasing on the time interval 0 to 8. We're only supposed to be studying the time the altitude's decreasing. You understand? Okay, so we have to be really careful actually with our limits of integration. That's where we got hasty, you see. It's right to integrate. It's wrong to include 0 to 8. So my guess is it's definitely not D. Also, the others have the wrong units. Look at some of these others. Look closely. This one says R prime. Wouldn't the units on this be meters per second squared? D second. So look at answer choice A. What's wrong with this picture? See what's wrong with it? The integrand is measured in meters per second squared. If we integrate that, what's that going to give us? Change in meters per second. That's not what we want, see? Same thing with this one. So we got it down to C and E, see? So now it really is a calculator exercise from this point on. How are you going to know when the balloon is losing altitude? You're going to need to graph the balloon rate equation. Okay, so let's get the calculator out again. And let's go ahead and type in our function. It's, might as well just be x cubed, right? Minus 4x squared plus 6. And we can graph that guy. They were very nice to us. It fits in a standard window. That is super generous. No zooming. It's ready to go. Very cool. I don't think times that are negative mean anything at all. So why don't we just go and make our window start with an x min of 0. We don't need to look at the left side at all. Now remember, what you're looking at right now is R of t and t, right? So you're not looking at a balloon, hot air balloon. You're looking at a velocity equation. When a balloon is moving up, the velocity is what? When a balloon is moving up, 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 velocity is what? Positive. When a balloon is moving down, 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 negative. So you're actually going to look at the aboveness and belowness on this graph. So that's what you're really looking for. So you're actually interested in when the altitude is decreasing. That would be here. See? When the velocity is downward. Yeah. Okay, so we need those 2 points, or you can just look at them. There's one of them that's between uno and dos. There's one of them that's between tres and cuatro. I don't even think I said that right in Spanish. But one's between 1 and 2, one's between 3 and 4. Let's go back and look at our answer choices. I'm going with C. Okay, how accurate does it need to be, right? We got it down to 2 choices. Quite a bit harder, right? You know why? That was a real question. Straight off the AP test. What do you think most people in the nation put? D. That's right. Because they didn't read the full question, right? Let's go to next page. This is so much easier. The second fundamental theorem of calculus. It just basically says that if you differentiate an integral, it returns the function. Like that. Okay, now maybe you've always wondered why that is. Let me show you really quickly. It's super easy to understand. Watch this. Isn't it true that integrating gives us the change in the antiderivative? True statement, right? Integrating lowercase f gives you capital F. You plug in the two limits of integration, x and a, subtract. Nothing new there, right? Capital F's the antiderivative. What happens when you take the derivative of a difference? You take the derivative of the first function minus the derivative of the second function, right? But a was a constant all along. A is constant. So this term is 0. F of a is also a constant, right? So this is the time of the year where you might actually think about why this is true. So this just returns df of x dx. And what's the derivative of capital F? Lowercase f, right? So it's not that mysterious, really. Some of these rules seem so complex, but they're not. Now, if there is a chain rule involved at all, that makes one extra step. Anytime you differentiate something that isn't just strictly x, you're going to need to do the derivative of the inside sort of thing. So you're basically going to do this. Watch closely. D dx of f of u of x minus f of a. Make sure you use capital letters on those f's. That's a u. Okay? The derivative of that is just derivative of the first one minus derivative of the second one. Remember, this is just a constant, so it's 0. So this gives you, what's the derivative of the outer function? Capital F. What's the derivative of capital F? Lowercase f, right? So this is just lowercase f with u of x in it, times the derivative of the inside, which is u prime of x. Right. Okay, there's actually a third version of this. Let me show you that real quick. Let's say you have d dx of, and then this down here is m of x, and this is n of x. This is sort of the most complicated they could possibly dream up. It doesn't get any harder than this one. But even this isn't that hard. Watch. It just becomes capital F of n of x minus capital F of m of x. This time there are no constants, so nothing becomes 0, but you take the derivative of the first one, you get f, lowercase, right, of n of x times n prime of x minus f, lowercase, of m of x times m prime of x. So we had learned this rule earlier in the year, but again, it's not that complicated. You could rederive it if you lost it, right? Just change the capital F, change it back to lowercase f. So hopefully I demystified that for some of you, unless you already knew that. Okay. It's no good though if you can't use it, right? So let's give it a try. And the AP test is really good at writing questions, so you'll find yourself needing just about every rule on this page when you do real problems. But here's just a quick drill. Notice it says find f prime. So if you're going to find f prime, you're going to d dx this side. So this just becomes x squared. You really do just take this and plug it in. Find f prime. So we're going to d dx. So what's my answer on this one, Michael? Correct. What's the next one going to be, Evelyn? That's right. And the next one is sine x, someone said, good. Okay, now we just gotta, on these next ones, just gotta watch that chain rule. Notice these are now functions. We're starting out simple, these are all x squareds, right? So, Joseph, what's our next one?
X to the 4
X squared squared, right?
times 2x.
Correct. So this becomes 2x to the 5th. The next one, this is f prime, right? Next one, Francine?
X to the 4th plus 4x times,
4x squared, right?
oh yeah, 4x squared times 2x.
Yeah, and the multiplication by 2x is sort of an afterthought, right? So notice that we have constants down at the bottom, so we don't actually ever have to do anything else here. Right? Okay, good. Remember when you plug in the x squared, it goes into all the t's, so both of these get affected by that. Right? The next one is what, Michael?
2x squared.
Yeah, square root of x squared, and then you end up multiplying by 2x. You're right, it's 2x squared. I had to think there for a minute. Thank you. And the next one is what, Evelyn? That's right. Some of them simplify, some of them don't, right? Good. Remember that this is f prime, so always title it. You don't want to think that this is f. Right? Okay? And I thought we'd just do one more slightly tougher example down at the bottom. How would you integrate from x squared plus 5x, or how would you take the derivative of the integral from x squared plus 5x to e to the x plus 2 to the x cos t dt? This is a ridiculous example, but if you can do this, you can do any of the ones they offer you on the AP test, I promise. Okay, so what's the first thing we do? Plug it in, right? So this goes in for the t, right? So we end up with cosine of e to the x plus 2x, or 2 to the x, I mean. Now we're supposed to take the derivative of that top limit. What's the derivative of e to the x? Right? What's the derivative of 2 to the x? 2 to the x, ln 2, good Evelyn, minus, now we'll do the lower set down here, see? Same thing, plug it in again. So cosine x squared plus 5x. And what's the derivative of the inside? That's easy. 2x plus 5, right? So there it is. So if you can do that, you can do any of them because, well, I've never seen them even that complicated on the AP test. They're very simple. So we like those problems. They're easy. What's that? Yeah, so it feels like we're just substituting. And the reason is we're actually taking the derivative of the integral, right? So when you take the derivative of the integral, in a very real sense, they just sort of undo each other. You know what I mean? Now you don't actually get f of t, you get f of x, as I tried to show earlier up in those boxes at the top. We actually derived why it comes out to f of x and not f of t. But it really is just kind of canceling out on us. And I'm not totally done with my math history studies. I have a class to take. But from what I understand, there's one more class I need to take called math history. And I think the order went like this. They actually discovered first that this was giving them f of x. And when they realized that, they then realized that integration is the opposite operation of differentiation. So that was actually historically how it happened. We think, oh, well, it's just derivative integral. Of course they cancel out. No. Once they realized this was true, they suddenly realized, oh my goodness, integration and differentiation are sort of opposites. See? So to us that seems really weird that they would come to that conclusion, but that's where they perhaps found out that doing an integral area is related to antiderivative. You know, historically that had to happen sometime, right? Very cool. I need my eraser. Where is it? This thing's really hard to use today. Let's go to next problem set. These are real test questions, and you can see they're easier than the one I just created. But they're so good at writing distractors, you almost feel like you're doing them wrong because they're so easy. You'll be tempted to second guess yourself. So let's look at 1969 BC 12. Don't second guess it, you already know how to do it. What's the correct answer? E. You plug the X in. Can you see though why some people might get carried away and think they have to do like something else, right? The answer is simply E. So they're really good at writing distractors. Although I'm not sure where they dreamed up C there. Look at that thing. Look at that mess. It is interesting. Okay, 1985, AB 42. See? You sure about that? Yeah, don't second guess yourself, right? It's 1 plus x squared on the inside of that square root. There's nothing else to do. You know people get these wrong because they don't review the rules, right? Okay. Next is 1988. BC 14. Okay. Okay, now we need the chain rule, right? We've got an x squared up here. That just means there should be a 2x on the outside. Oh, and that's not going to be an x cubed, is it? It's going to be an x to the what on the inside? So what's the correct answer here? Yes. It's getting a little harder, actually. Look at 1993. Finally, a good question. The AP test has been going for 40 years, since the 50s, and now they finally created a really good question. This one makes us think. And it's been that way ever since. Since the 90s, this test has been a lot harder than it used to be. You should see the 1970s something test. It's like pre-calc. Really, not kidding. Okay. Play around with that one for a minute. That'll stretch you. So here at 4 o'clock, we'll start in on the real questions that are like free response stuff. That's where they really stretch us. Okay, so the first thing is, if you're going to be finding a minimum, most of the time in calculus, you're supposed to set the derivative equal to 0. There are some exceptions, like where that's not what you're supposed to do. Let me tell you what they are real quick. If the function is not like differentiable, and there's like these weird corners or cusps, sometimes those create minimums too. But that's not happening to us on this problem. I'll tell you why. How many of you know the antiderivative of e to the t squared? Anyone know the antiderivative? Didn't think so. Okay, but e to the t squared, does it have any domain exclusions? Are there any t's that can't be plugged in? Can you think of any? I don't think we can think of any domain exclusions, right? T can be any number, t squared can be any number, e to the something, you can plug in anything into e. E is a hungry creature, although he only spits out positives. He'll accept anything. You can give him anything. So, what I'm saying is E is so continuous, and there's no breaks anywhere. That means that the antiderivative, right, is smooth everywhere. So the continuity of the integrand ensures ensures a smooth differentiable function. No corners, no cusps. This is the right thing to do, which was probably your first thought. So this is exactly what we should do. Go ahead now and take the derivative. So you're differentiating this integral. So you're actually finding f prime and you're ddxing here. So notice you don't have to solve the integral. You're just going to substitute this in. So you're going to have basically e to the garbage squared times derivative of garbage. The constant at the bottom means we don't have to do anything else, equals 0. Okay, now e to the garbage squared, that cannot be 0. That's impossible. But 2x minus 3 could be 0. So what is my only critical point for this problem? What's the only critical point? You have to look here. What's your only critical point? 3 halves, right? Before you circle answer choice C, are you sure it's a minimum? Just because the derivative is 0 does not mean it's a minimum. So this question is so much better than the other ones. It could be a minimum, but when a derivative is 0, it could actually be a maximum, it could be a minimum, or it could be a point of inflection. So don't be too hasty. You need to now check. Right? Okay, so here's your derivative right here, all of this. So you can just plug in a number to the left of 3 halves, a number to the right of 3 halves. We'll just turn this into a sign chart real quick. F prime is right here in the red box. Don't worry about the E part. That's always positive. But if you plug in a number less than 3 halves, you're going to get what? Let's say you plug in 1. You're going to get a negative first derivative, right? Okay, so this is negative. And if you plug in, let's say, 2, which is on the other side of 3 halves, your derivative is going to be positive. What does it mean for the derivative to go from negative to positive? It's falling and rising, yeah. So it is a minimum, it is C, but don't be too hasty. The answer easily could have been A. We had a 1 in 3 chance that 3 halves was a minimum. Good question. So much better than 1988. Okay, let's go on to... I don't really like the next question at all, so let's go to the next page, actually. I didn't like the wording. Yeah. Okay, so this is kind of the good stuff. And I think you've actually done, on the next page, I think you've done this one before on the next sheet. So we're just going to do this page, and I think that's it. Or maybe there's one on the next page I might glance at. But in our last 15 minutes or so, this is definitely worth our time. These people are great question writers. So I'll give you a few minutes just to digest all this. Okay, so what's really important is you understand that this is saying if you want to find like g of negative 1, you're going to literally replace the x with negative 1. That's really important. Okay? Now whoever puts their lower limit of integration has a number bigger than their upper. So you're going to switch these around now. Okay? So switching those will give you an extra negative, but it will make it easier to understand. I meant to switch them around. So I was going to put the negative 1 at the bottom, the 0 at the top, just because it's more meaningful to me. So negative 1 here, 0 here. I think all it's asking you for is this area, right? This part of the problem is asking for that area. Okay, so that's just a 3 by 1 triangle. It's got area 1.5. So the answer to this is negative 3 halves. Did you guys get that far?
Yes.
Great. Okay, g prime of negative 1 is an entirely different thing. Remember, you don't plug in the negative 1 and then take the derivative. You take the derivative, then you plug in the negative 1. Okay, so what we need to do is go back up here and write in what g prime is. So g prime is d dx of 0 to x f of t dt. In other words, it is what? F of x. Ah, interesting. We have a graph of f of x, right? Okay, so if I ask you for what is g prime of 1, that's an entirely different question. It's really asking for f of 1. It's the same thing. See, g prime is f. This is a graph of f, but it is also a graph of g prime. So let's retitle our graph. It's not only a graph of f, it's also a graph of g prime. That is very helpful. Okay, now we know what we're looking for, the y coordinate, right? Ah, so what's f of 1? Just look at the picture. I meant to write -1, thank you. So it's 0, isn't it? I told you they're good test writers. Okay, what is g double prime at -1? You could also think of that as f prime at -1, right? It's the same thing. How do you read f prime from an f graph? You look at the slope, that's right. So what's the slope of this line? Just count the rise and run.
Oh.
It's 3, right? What a great question. It's an excellent question. It's a very cool question. Wish I could write tests like that. That's just great. I'll bet you get 3 points out of 9. This is important, listen. 3 points out of 9 on the free response, because this is a 9-pointer, and you probably just got a third of it, and you probably just beat the national average. Because most, most free response questions fall between 2 and 4 points out of 9 on the national average. So imagine if you got a good score on the multiple choice, and you got 3s on every free response. That's actually pretty darn good. Okay, we're shooting for 9 though, right? Is there any part of this problem that you would mess up on? You think you could do this again? I really think you could. In fact, you don't have to start with this graph of f. You could draw any graph of f and play the same game. Okay? All right. Let's go now to part B. So, for what values of x in the open interval -2 to 2 is g increasing? Okay, I gave you a page of sentences a while ago. Okay, you might remember this document. This is such an important document. Okay, it's just full of synonymous phrases. For example, I know, Michael, you're familiar with me harping on this sheet. This sheet is so important. If I say f prime is positive, that means f is increasing. If I say f prime is negative, that means f is decreasing. And there are many synonym phrases for things. So there's another way to say what they're asking for. They're asking us for when is g increasing, but there's another name for that. What is it? G prime is what? Positive, yes. We have a graph of g prime, don't we? Beautiful. Yeah, it's just their f graph. So go back now and answer the question. Simple. Yes. So we're looking for the aboveness on this graph, right? I like to call it aboveness. So what interval does that happen on? Right, -1 to 1. Now you have to explain your reasoning, okay? So you would say g is increasing on the interval -1 to 1 because, what's our reasoning? Yeah, the graph, you could just say, you probably could just get away with f, right, which is g prime, is positive. They love that. When you reference f being g prime in the sentence like that, they love that. Okay? That's what they're looking for. They're looking for you understanding multiple interpretations of one graph. Alrighty. For what values of for what values of x, in the open interval is the graph of g concave down? There's a synonymous phrase for g concave down too. Sorry, that's the wrong document. There it is. Concave down. Let's search our sentence document for that. you already know. Here we go, right here. If f is concave down, f prime is decreasing. Same phrase. It means the same thing. For f to be concave down is for f prime to be decreasing. For g to be concave down, it means g prime is decreasing. We have a graph of g prime. I'll give you a sheet if you want here at the end. Gotta go? I'll print it for you now then. Okay, so we're now looking for where the graph of g prime is decreasing. So that's this part. You're welcome. Have a good weekend. Where is g prime decreasing? That would be from 0 to 2. So we're going to write the same thing as before. G is concave down on the interval 0 is less than x is less than 2, right? Because g prime is decreasing, or f equals g prime is decreasing. They love it. What do we got? 6 out of 9 points? This is not hard. There's no calculations at all, except that triangle at the beginning. Is there a part D?
Yeah.
Of course, they're always going to give you something that really takes a lot of thought, not just interpreting graphs, but using them to form equations and stuff. So what's our part D say? I can't remember. Okay, so what have you learned about G? First of all, how was G defined in the original problem? G was the integral from 0 to x. Was it 0 to x?
Yeah.
Okay, f of t dt. Okay, here's the thing. You know where G is increasing. You know where G is concave up. You know all this stuff about G, but you don't know any coordinates. You don't know a single point. Can you think of one value of x that would give you 0 here? What x would you plug in right here? This is very important. Watch close. What x would you plug in right here to get 0?
2. The negative 2.
No, I meant into the integral.
Uh,
Yes. So if x equals 0, g is 0. In other words, g contains 0, 0. Okay, that wasn't necessarily obvious, but you need that. If you don't have one point, how are you going to draw upslopes and downslopes and concave downs and all that from a point? You don't have a point just to reference, right? Okay, what else did we learn? What did you learn back in part B of this problem? It was increasing from -1 to 1. So that means you kind of need to give it some rise, don't you? What else did you learn? This is a rough sketch, right? We'll tidy it up as we go. What did you learn in part C? G was concave down on what interval? Okay, so it sounds like we're going to need to make it sad between 0 and 2. Sad, so like that. I don't know, does it hit the x-axis? What did we find back in part A? Part A, didn't we find 3 different facts? What x-coordinate did we use in part A? Go back to part A. We said that g of -1 was what? What was it? Yeah, -3/2. Ooh, that's a point, right? -1, -1.5. So I guess we did have another point. That's cool. Let's plot that point. -1, -0.5, 1.5, right there. Okay. What else did we learn back in part A? G prime at -1 was what? 0. Ooh, what does that mean? That's important. The slope is 0. That must be a minimum or something, right? Okay, what else did we learn back in part A? G double prime was 3. That just means concave up, right? We don't really know what concavity 3 means, but we know what concavity positive means. So the graph is happy right here. This thing's really shaping up, right? Do you notice any interesting symmetries on your original graph? Does it contain any symmetries? Y-axis symmetry, doesn't that mean it's an even function? Doesn't that mean that the antiderivative would be odd? It would have one more degree, right? Ah, so we know the symmetry here too. It's an odd origin symmetry. I think we just got another point for free right over here. I wasn't too sure where to plot my y value over here at 1, but I now know it's at 3/2. So this point I knew. This point I get for free from symmetry. See? It's all shaping up. Do you think it maybe hits the x-axis here and here? I think Joseph thinks it does. What makes you think it hits the x-axis here?
Well, what I do is I plug in like values for x
Yes.
into the original function.
Okay. Yeah, so
And it was
you can kind of do this at whatever stage you want. You can kind of start by making a table, if you want. Or you can just add points as necessary by making a table. But technically you can find any one of these points. So you can just go, the integral from 0 to -2 of f of t is the area between 0 and -2. And this actually comes out to be 0. If you look back at your original graph, you'll see the area between 0 and -2 actually cancels out perfectly. Yeah, so this point is -2, 0. If you actually integrate to -1, you get the -3/2. We did that back in part A. Obviously, if you integrate from 0 to 0, you're going to get 0. If you integrate from 0 to 1, you're going to get this 3/2. And if you integrate from 0 to 2, you're going to get 0 again. One last question. Should I make it smooth? Because I've obviously made it quite smooth. Do I have any justification for keeping it smooth? Or maybe these should be corners, you know, like sharp turns at the top. What do you guys think?
but there's a derivative.
What do you mean?
G prime of 1 and G double prime.
Yeah, you don't want to make these sharp turns, right? Because then there'd be no derivative. But we know there's a derivative. You can see it in the picture above. So the continuity of the graph they gave you at the top, the fact that it is fully connected, means that this is fully smooth. So we round it out, smooth it out, and that's our graph. 9 out of 9. You can do it, for sure. And if you get a 9 on one problem, that really boosts your average on the free response, right? Yep. Let me just see if the next page had any goodies in our last few minutes here. I need that one. We've already done this problem, right? I assigned this problem for homework, although I never recorded a solution. You can go on Google and just type the name of the test. You probably already know this, but this is another free response, another real one. Oh man, which year is it? I can't remember. Do you guys remember what year it was?
2003.
I think it was 2003.
Yeah, I think so.
Well, no, you took the 2003 test a couple Saturdays ago.
I was just kidding.
I don't think this was on there, although it looked a lot like this one. 2005, maybe. But anyway, you can definitely go to Ask Mr. Calculus, and he has a website where he has posted every solution to every multiple choice and free response problem since 2000 or so. Yeah, so you can find the solutions to it. But this is another good one to do. This one's a graph of G prime, so they're not giving you an integral expression. It's just a different variety. You could probably do this problem all over again and not remember it, so.